Trying to share very well. All right, here we go.
Yeah, it's okay. Yeah.
All right, perfect.
Nice.
Well, then, thank you, everybody. Thank you for the invitation. Hello, welcome, everybody, to my talk. I will be talking about the title of my presentation is Physics-Based AI is Revolutionizing Soiling Estimation and Cleaning Optimization in Large-Scale PV. And we have had a few, well, my previous presentations have been mostly about questions during the operational phase of the power plants. What I would like to go into a little bit now is how can we use methods like AI, like machine learning, to predict conditions during the design phase of the power plant and prepare in the most optimal way to mitigate them, maybe as early as the design, and then be prepared to when they occur during operation. All right. Okay, so what I want to do is the presentation has 4 parts. First, I would like to give you a brief presentation about who we are and where we come from and what do we do. And then I would like to quickly describe the problem and better define the problem a little bit by explaining why it is important to assess soiling and optimize cleaning as early as day 1 of the design phase. And then I would like to show you how data, algorithms, and AI can help us solve these problems as early as day 1 of the design phase. And then finally, I will give you some examples from our work, some results from different conference presentations where we have also shared results. Okay, so that, our motivation. So there have been reports, or there are reports, and maybe some of you in the audience that are operating PV power plants know that once a power plant is built, their performance is a little bit less than what was expected during the design phase. So in this report by PV Magazine and Kilowatt Hour Analytics for data in the US, they found that an average power plants are underperforming by 8%, which is a lot. And the problem is, we are of the opinion that one of the problems is, or the big problem is that people or the project developers, when they are designing their power plants, they have they rely their estimations on input values for example, soiling, that do not have no very strong relation to the reality and the site conditions of their project. So what we want to do, or what we're doing at PVRADAR, is we empower project developers to achieve world-class performance and reliability across all climatic zones, transparently and traceably, and most importantly, we do it as you can do it as early as the first day of the design. Right. So what does that actually mean? We, in our activities, is separated into 3, or for now, we have 3 different fields or topics that we are interested in. The first one that I will be mostly talking about today is soiling risk assessment. So a project developer would like to know what kind of conditions they will face at the specific location when new project is planned, to best prepare for it. Now, once the conditions are known, what we want to do, or what is needed, is to perform a cleaning cost optimization. That can be done very early to decide, for example, whether it makes sense to buy a tractor or to invest into a robotic cleaning system, or whether maybe manual cleaning is enough. And then there's a third topic that we're interested in, or that we're working on, that is the question of albedo improvement. Also a question that during design, especially in locations that are very dry and arid, it makes sense to consider those geotextiles or white plastic surfaces below bifacial modules that enhance the reflection of the ground and therefore yield additional energy and usually pay for themselves after just a few years. During my presentation today, I will be focusing mostly on soiling estimation and cleaning cost optimization. Right. So just in a nutshell, what can you expect when working with us? So the kind of results or deliverables that we provide, there is linked to our first topic, the soiling risk estimation. What we do is we develop, or we deliver reports for a specific location. You can request a report for a new location that you're interested in. And basically, what you get, you get a report that, of course, contains our methodology, the data that was used, the justification, but most importantly, you get 12 accurate monthly average numbers for the average soiling losses that you can expect at that location, and that you can then feed into your PV Assist to get a much better estimate of what kind of soiling you would have to expect at that location, instead of using maybe 2%, that is a standard value from PV Assist itself. Now, once you know what the kind of soiling problem is, you would like to do something about it, and then you can use our get a license for PVRADAR online or PVRADAR platform, with which you can optimize the cleaning for that location, and therefore bring down the soiling losses and the 12-monthly soiling loss factors to a much lower level, but of course at the expense of cleaning. And there we make sure that this cleaning is as little as you need to, as little as possible, as cheap as possible. What you can also use this for is if, for example, you have a new power plant and you have to select a cleaning technology, maybe you want to buy a tractor, and there are many different offers, and it's very difficult to compare apples with apples. But our software helps to decide how much more, for example, would you be willing to for a cleaning technology that has a slightly higher cleaning efficiency, and how to compare this, a tractor maybe, against a cleaning robot that works very differently, and where the comparison is not that easy and you cannot just go by price. And then finally, what we're working on is during of course, soiling and cleaning are important during the operational phase as well. What we have there is we build software. Our tool enables the operating team to make decisions during the operation of the power plant based on forecasts. And this is where most of the AI comes in, based on forecasts of the soiling development, so that you can decide on which date is the most cost effective for the next cleaning. Before I go into the real presentation, we just quickly introduce us and the team. So this is the founding team of PVRADAR Labs. That's myself and colleague, former colleague and now partner, Franco Clandestino. We both have worked at big French energy companies. So we have been in the position of, well, our previous position, we were asked to support business units in making these kind of estimations and helping business units to build better power plants, build more cost-effective designs. And what we realized during the time is that very often the tools aren't there, and therefore we decided to build PVRADAR, and we teamed up with Konstantin Pogorelov, a very capable software developer, and his team. And this is how, and together now we develop tools that really solve problems. We were founded in 2022. So far, we have had quite some success with a total of more than 50 projects analyzed for our customers, totaling or summing up to more than 4.5 gigawatts of plant capacity. And maybe just an interesting, we are a very international team. We speak a total of 7 languages amongst the 3 of us. All right. Now, the more technical part of the presentation. Why is it important to assess soiling and optimize cleaning during the design phase? And that I would like to explain with a little, comparison. So let's assume we are in the early design of a power plant, or what I would like to show is what can go wrong if you don't, and then of course what we can improve upon. So let's say we are a project developer working on a new project in Morocco, let's say, and unfortunately, for that very location, there are no measurements available, and also there's no time. Usually you have to make a bid, maybe you're participating in a tender, there's a deadline, you need to make a yield estimation, and for that you need to know what kind of soiling losses you would have to use. So there's no time to do the measurements, therefore you make a guess, and you could go with a 2% from PVSIFT or something else, and usually what people guess is something flat for the entire year. So a certain percentage, same in every month. And that might lead to underestimating of the production, but very often what happens is that people take a number that is too low, and therefore in the end, what happens, what I started my presentation with, the plant performs less well as it was expected beforehand. Right, then so that is during the very early design. Now let's say the power plant moves one step further, and we already are basing our expectations based on wrong assumptions. But now our EPC team needs to determine, create a cleaning or incorporate a cleaning strategy into the design. They may either think that the problem is that there is no problem. Therefore, a very small cleaning budget is being associated to the plant, and then people in operation later find it very difficult with a very small budget to maintain the high expected performance of the power plant. And that, of course, is a problem, because at that point, many of the options that you had during design, they're already gone. Alternatively, the EPC might also think that soiling is a very big problem, where in reality it is not. Happens less often, but may happen as well. In which case, yeah, there is a good cleaning strategy. Well, the intent is there to incorporate a cleaning technology into their designs, and then you would get quotes from many different cleaning providers and find out that prices are very different, and it would be difficult to make a decision. And you might turn out to just go for the cheapest one, because prices are of course easy to compare, but not necessarily for the most for the best quality, and that then can again leads to problems later on. So what is the solution? The solution is to incorporate data as early as possible, and then therefore be able to make data-driven decisions. Again, I know I repeat myself, but it's something that I learned the hard way. It's important to start as early as possible to avoid very costly reiterations. Like the later design needs to be changed, the more costly it is. And once it's in operation, changes, even adding a cleaning system might be very difficult. And then, of course, once the power plant is being built, right, you have a good estimation, for example, provided by us. But then during the operations, you still want to measure soiling, you still want to have an open eye for it, and then fine-tune your cleaning strategy during operation. That might still bring benefits. Okay, so how do we help our customers achieve this? So we do this with three different. Well, I already mentioned. So we have this. We have the soiling report that gives you the soiling loss factor, along with a very detailed documentation that you can then add to the project documentation, share with banks, share with shareholders, and it gives a lot of transparency and a lot of credibility to the project. We help with our software. It is possible to make a holistic techno-economic optimization of the cleaning strategy for that power plant, and to determine which technology is the best and also which cleaning frequency is the most cost efficient. And then the solution that we're building during the operation then helps to fine-tune that and really decide case by case, year by year. Okay, in this case, now it rained a little bit more than last year, so we will do the cleaning a little bit later, and that still gives a little bit of a benefit. All right. With that, let's jump into a little bit more of the theory behind and the underlying models. Or I would just go through the process of doing the soiling assessment and the cleaning optimization theoretically once, and then at the end I will show you some examples of results that came out. All right. So how can data, algorithms, and AI help us to solve this problem? Just to make sure that this is very well understood. Okay, so what is the theoretical problem? What we want to do is we would like to make a cost optimization in the end, to find the optimal cleaning strategy. And the optimal cleaning strategy is the kind and number of cleanings that brings down the total cost, which is the sum of the cleaning cost, of course, and the energy loss. If I clean every day, that is optimal in the sense that the power plant is never dirty, but of course that is might be way too expensive. Most likely it is. And then there's the other extreme where I clean never. That doesn't cost me much, but also there will be a lot of soiling losses. So the optimum is somewhere in between, and where exactly that optimum is depends on the soiling conditions, the meteorological conditions, irradiance, most and foremost, the PV plant technical design, of course, the market environment, at what energy sales price am I selling my energy? Then the parameters of the cleaning technology and the cleaning cost for the cleaning strategy that I have chosen. And in our software, it is one is able to input all of these inputs, and the rest, which one can't input, they are derived by our machine learning algorithms. Right. So how does it look like? What are the steps in our solution? So the first step, you would have to select the project location and define the design. Of course, depending on the location, if we're in the middle of the desert or in a more temperate place, soiling may be very different. For example, what we have seen in power plants in dry and arid, maybe, well, for example, in Morocco, I would assume, This being the case, the soiling is there's a lot of mineral dust in the air, which means that the soiling does accumulate rapidly, but once there's a rain, it kind of gets rid of the soiling again, leaving the modules more or less clean. Whereas in places where you would not think of soiling as being one of the biggest problems in the first year, it happens that, for example, in Germany, where I live, it happens that soiling builds up very slowly year after year. There's a layer of very sticky plant material building up on the modules that even though it rains, it never really goes away, and you can only clean it away with mechanical cleaning. And therefore, of course, and this is very well defined by the location, of course, and also the plant parameters, tilt angle, and so forth. Now, then for that location and for that technical design, we run a soiling estimation, and we do this with on the basis of historic data. So we go about and collect from different sources, meteorological data, the ambient temperature, wind speed and direction, humidity. Most importantly, we go and fetch 20 years of historic concentration for different components, particles, suspended in the air, for the very location. And also we fetch information about the rainfall that this region has seen. And all of this we combine in our soiling estimation model to get a historic soiling profile. I will show an example how that looks like at the end. With the soiling profile at hand, we can then compare, or once we know what the soiling problem is, we now would like to compare different cleaning technologies. So a user in our software has to select what are the different cleaning technologies that one would like to see in the comparison. And what we offer, or what the software is capable of simulating, is dry cleaning robots, dry and wet, cleaning tractors, also dry and wet. There's fully autonomous cleaning robots, manual cleaning. And all of these systems are described with their lifetime, the lifetime of different components. Of course, if you clean more, then of course your brush will be worn out sooner, and then you have to replace the brush. All of these costs, all of these implications are considered in our software. You need to have the cost, the operational parameters, and of course the cleaning performance, most importantly the cleaning efficiency. We offer a database of available cleaning systems, but users are always able to fine-tune every single value if you think you have a better estimate, or just would like to find out what happens if the soiling cleaning efficiency was a little bit higher, a little bit lower. You can, and you immediately get the impact on the total cost of ownership of that system. What we're also experimenting with is including other mitigation strategies than cleaning. For example, anti-soiling coatings could also be modeled, but that is a feature that is still under development. But if you're interested, we can talk about that as well. Right. And now comes, so we have to find the system. We have to find the historic soiling conditions. We have to find what kind of cleaning is available to us. And now what we want to do is we want to make a forecast, a long-time forecast, 20 years into the future, to find out what will be the optimal cleaning strategy. And this is where machine learning techniques and AI come into play. And here, I don't have much time to go into detail, but there is basically two approaches where you have a data-driven approach in AI and a more physics or a model physics-based approach. And we're in favor of the latter, as we think that the AI is great in certain occasions, but still it is necessary to make sure that the outputs of that model suffice physical reasoning and they are physically possible, and that we make sure with that approach. Finally, so again, where are we now? We have now our estimation of the soiling conditions in the future, and what we do now is we test for the different cleaning technologies, different cleaning packages that have been selected. We find out what is the optimal number of systems, what is the optimal number of cleanings, what is the optimal date at which it needs to be cleaned, and that of course can be different in every year. And the result is a total cost of ownership for each of the alternatives. You see in the bottom, you see the stacked bar plot. In red is the soiling cost. So even though you're cleaning because you cannot clean every day, there will be still some residual soiling losses, which have a cost. And then in blue is the cost, the actual cost paid for the cleaning. And of course, you have to consider both. And we find in red, that is the scenario you do not clean, you never clean. We find that that is our base, base case. And then in this case, in this example, there would be 3 systems that are better than never cleaning, and 1 that is actually worse, more expensive than cleaning. Again, there will be an example. And I think, well, speaking of examples, now let's jump into some of the results. I lost track. Oh, I think I'm a little bit over time. Sorry for that. Well, yeah. So here's an example for a power plant in Portugal, where we combined, where I think the results that you have seen before, they are from that power plant. So in this case, no cleaning, or what you can read from this is that for this power plant, the scenario of no cleaning is actually not the best one, and you would like to clean regularly. And the best that we have found was a wet cleaning tractor, 3 systems with an average 2 cleanings per year that would increase the levelized cost, the net present value of the project by 742,000 euros. Yeah, so a considerable or a nice improvement that you would like to take. These were results that we presented at the EU PVSec last year. I also have some results from the Middle East and North Africa Solar Conference, the MENA SC, where I presented this plot. This is a soiling profile for a power plant, I think in Oman. As you can see, based on the historic data, you see, yeah, the soiling conditions are not the same in every month of the year. In January and, well, between October and February, maybe they're a little bit lower, and then they increase, reaching their peak in August usually. But as we can see in the spread, every year is a little bit different. And that, of course, it makes sense to consider in your modeling. Otherwise, you would be cleaning at times where it's really not that necessary, and you should really put these resources in months that see more soiling. Finally, I can show you a comparison of different models and validation data. So we compared our prediction models with measurements for a site in Spain, and you can see, well, there's 4 different variations of well, we have different algorithms. We were experimenting a little bit with different algorithms, different models, and you can see that by tweaking the input parameters, and this is something done by BI as well, or by our methods, by tweaking the input parameters of the model, we can have quite a good fit, not a perfect fit, but quite a good fit, and a much better fit than one would have guessed without any knowledge, which is unfortunately very often the case. And with that, I conclude my presentation. Please have my email here. If you have any questions, well, you can reach out to me or ask me now.